Let's continue. Let's talk about differentiability again and continuity. So the next thing we want to look at is the concept of continuity had to do with, so when you look at continuous functions, the key idea is that the limit of f of x as x approaches a equals f of a. So we've seen that before. That's the basic concept. But just for my proof I'm going to do in a bit here, notice that I can rewrite that as the limit of f of x minus f of a as x approaches a. If that's equal to 0, then that's an equivalent statement. Okay, so we will be using that. So then when you look at this theorem, just write it up right here. I was talking about this in a previous video. It says if f is differentiable, then oh, and now I did say add a value because you can extend that to any interval after you have this one. If f is differentiable at, we'll say c this time, x equals c, then f is continuous at x equals c. So we saw above on this one right here, this one we looked at, it's continuous, but it's not differentiable because you get two different limits on either side of 4. So this is not differentiable at 4. It's differentiable everywhere else, but not at 4 because of this. So the differentiability means that the limit is the same on either side. So, okay, we're going to use that. So then, but this says if it's differentiable, then it is continuous. Now, a little bit of logic stuff here. This is basically a P implies Q statement. So if P, then Q. So the the converse is Q implies P. Now, of course, those are not logically equivalent. Okay, so we'll use this for logically equivalent. Those are absolutely not logically equivalent statements. So the example I like to use sometimes, let's see, which one do I want to use? So if I say, if it's raining outside, then the grass will be wet, right? So if it's raining outside, the grass will be wet. Now, is the converse true? If the grass is wet, was it raining outside or is it raining outside? And you know that's, of course, false because you could have the sprinklers on, right? Or you could even be just like morning dew. But the contrapositive is always true or logically equivalent. So the contrapositive says if it's, so that's basically not Q implies not P. Like you flip it and then you make it their negations. So if you go back to my little example, if it's raining outside, then the grass is wet. The contrapositive would be if the grass is not wet, then it is not raining outside, which of course would be true, right? Always. You don't think of little examples of, well, what if there's a covering over the grass? I'm not getting into that stuff. It's just a basic concept. If it's raining, it implies water falling, kind of thing. All right. So converse though is not true. Okay. So not logically equivalent. Contrapositive is logically equivalent. Okay. So a little bit of logic there. Truth table stuff. Look it up. You don't have to, but someday you should. Okay, so let's look at the proof of this. So you say proof. First thing we're going to do for a P implies Q type statement is the if statement. If f is differentiable, then f is continuous. So you have to assume the hypothesis, which is that f is differentiable. So let's state that. You say assume f is differentiable at x equals c. Okay, and that's the first statement. So if you know it's differentiable, then we know that so if f is differentiable, then what we get is that this limit is true. Where's our limits? So differentiability implies this limit exists. Where'd it go? It's way back here, isn't it? We're going to use this one. Okay, then that limit exists, basically. So it's differentiable, this limit exists. Okay, so this is what we want to but what we want to show, though, okay, so now we're going back to this. This is what we want to show, that the limit of f of x minus f of a as x approaches, well, c in our case, is equal to 0. So we're going to actually start with that and then build what that looks like. So here we go. So what we have then, we're going to start with this limit and see what happens. We're going to say the limit of f of x minus f of c as x approaches c equals what? Well, if we show that that is 0, we're done. That's exactly what we need for continuity, right? Differentiability implies continuity. So if we can show that this is equal to 0, then we're done. But we don't know that yet. That's what we're going to need to build. So what we're going to do is we're going to multiply by x minus c both in the numerator and the denominator. Okay, so right, I just multiplied by 1. You're never actually getting to c, so you can actually do that. So you don't have to worry about that that use. And then f of x minus f of c. Okay, and that equals, then now what you have is you have two separate products. So the limit of the product is the product of the limits. Right, so you apply a property and you can say the limit of x minus c as x approaches c times the limit of f of x minus f of c all over x minus c as x approaches c. So now, oh, then what is this defined to be? What is that? That is f prime of c. So that's just f prime. And does that exist? How do you know that exists? Like, is that 0? Is that infinity? Is that undefined? Well, this is exactly the definition of derivative that we are assuming is differentiable. Okay, so differentiability implies this right here, this thing right here exists. Okay, so this is equal then to, the limit of x minus c as x approaches c times f prime of c. So f prime of c exists and is not infinity. It exists. It's just a number. It's just this guy right here. This thing right here is just in the reals. So what's happening to this then times something that's just in the reals? Well, this thing approaches what? What does that approach? That approaches 0, right? So that is 0. So you get equal to 0 times f prime of c, which is, of course, 0. And that's it. That's exactly what we wanted to prove. Therefore, the limit of f of x as x approaches c equals f of c. And you don't have to say this, but and is continuous. So that's it. Differentiability implies continuity. All right, so that'll be used in quite a bit of stuff in the future. Sometimes, depending on the type of class I would be running, this is a proof I'd want you to do, or I'd set it up and then you would prove it. So this is the type of level of a proof I want you to, maybe with slight coaxing, be able to finish and make us an argument on it. In our formatting of the class, you just copy it, so I'm not going to really ask you it. But in the future, if you really want to know this stuff, you should be able to do this proof on your own. Okay. So now we go on to the basic differentiation rules. So these rules are what we need to make this easier on us. So we're about to develop rules to make this easier. So basically all this stuff above, not all this stuff, but most of the stuff above, you only do this if I ask you to do it, or the book does for homework. Okay. Otherwise, you're going to use these properties. Okay. So make sure you make a note of that, because it's going to come up. I'm not there to tell you, in person. So things like that happen in this format. Okay. So these are what we call basic differentiation rules. So there's probably a list somewhere, and I'll probably get that list out eventually. Yeah, but for now, we'll just go through a few of the important ones. And then I think I'll pull it up maybe in the following video where that is. Okay, so where am I at? All right. Okay, so here's the theorem. Let's let C be a real number. So it's just a constant. So a constant or fixed, we call it. So these are just different terminology basically. So C is just real, and I was saying that it's a constant, or I should have said or what we say fixed or a constant. And we're going to say f of any value, or f of c is equal to, f of x is equal to c. F of any value is equal to c. All right, so then the theorem says basically the derivative. So if f of x equal to c, then f prime of x is equal to 0. So the derivative is equal to 0 of a constant. The derivative of a constant is equal to 0. So let's look at the proof of that. So when you look at these properties, so if I put like 4 there, in other words, like let me do an example first. So for example, if I have y equal to, let's just do pi. Pi is a constant, right? Then y prime is equal to 0. Derivative of a constant is 0. So let's look at that proof. So basically, if you just do the limit of f of x minus f of c all over x minus c as x approaches c, that's equal to the limit. Now what's f of x? What's f of c? Well, f of anything is just c. You just get c minus c over x minus c as x approaches c. That's equal to 0. I mean, I didn't even take the limit. It's just, you just get, this is 0 no matter what x is. So you don't even care what the denominator is. You're always going to get 0. So that's it. So therefore the derivative is just that. Okay, so here's another one. I'm going to show you the power property. Well, in this, I'll just go ahead and write it up. All right, so here's the power property. This is one of the more important properties of polynomials and stuff. This is called the power property. Power property says d dx of x to the n is equal to x to the n minus 1. Oops, sorry. Messed it up. Is equal to n times x to the n minus 1. So basically you bring down the power and then you subtract 1 from it. And this is actually true for n is any real. The book, I think, defines it like a natural number and stuff. You can define this later to be any real number. So you can actually say like d dx. Let me just do examples. Sorry, we'll just do some examples. Okay. So for example, if I have f of x equal to x to the fifth, then f prime of x is equal to what? Well, all you do is bring down the 5 like that. And then it's 5 minus 1, which of course is just 5x to the fourth. So that's the derivative of x to the fifth, right? That's using the property and not the definition. So if you use the definition on that, expand that whole thing out, divided by that h, you get an h to cancel, you'll get this. It's kind of messy, but you would. We're not going to do that unless I ask you to do that. Okay, let's do another one. Oh, I was going to show you, like, if you had even like g of x is equal to x to the like pi or something, then g prime of x is the same thing. You just bring down pi, it's x to the pi minus 1. So you still have the same thing regardless of that being an integer or not. It can be a real number. Okay. So let's go ahead then. Let's do another one. Let's do another example. So if I have y equal to x to the 1/3. Okay, and that's one of the examples that I had you do back here, I think. Yeah, this one. Check this one out. X to the 1/3, and I had that notation right here, or I think I wrote some stuff up. That's what you should get. This wasn't the derivative. This was just finding the slope. Yeah, this was actually doing this and then evaluating at 0 and seeing that you get it's not differentiable at 0. But this is the derivative. That is f prime right there, or the derivative. So when I do y prime, same thing. You just say y prime is 1/3 x to the 1/3 minus 1. Well, that's just 1/3 x to the 1/3 minus 3/3, which is 1/3 x to the negative 2/3. And we often don't like negative exponents because it can be misleading what it really is. So that's just 1/3x to the 2/3. Okay, so that is your derivative of x to the 1/3. That's how you want to do it. You don't want to do that the definition unless we have to, which you will have to. But that's how you write it out. Okay. So this thing is differentiable. We'd say this is differentiable everywhere except 0. So at 0, it doesn't exist. But everywhere else it does. Okay, let's look at the proof of that one then. Proof of the power rule. We'll go ahead. It's going to take a while, so we'll come down here. We'll do that before we do more examples and more properties. Okay, so we'll just say proof of the power rule. So why does that work? I mean, you can't just go around making up these properties. Like, how do I know that works for the derivative? But, I mean, doesn't make any... I mean, I don't know why that works. I mean, I can't see the connection between this and the definition. You know, I don't really know. Like, here's the definition. Right, back here. Where'd it go? Way back here. Way back here. Here's the definition. Either of those two we can use to help prove this. It's not clear to me why that gives you that property. Okay, it shouldn't be clear to you. Well, I mean, unless you're a genius, but it's probably not obvious why this works. So we're going to show why this works. That's what a proof does. We only have limit properties, definition of limits, or concept of limits, and algebraic properties, and the definition of derivative to show this. So that's what we're going to do. So we're going to let, oops, I need to change that. We're going to let f of x equal x to the n. Okay, and then show f prime of x is equal to, this is just a reminder of what we're doing. So it's kind of all on one page. f prime of x is equal to that. So we'll start with, we'll just say d dx. And notice how I jump back and forth between the Newton notation and Leibniz notation all the time. You got to just get used to it. Sometimes it's nice to write it like that. Sometimes it's nice just to do the prime stuff. So d dx, x to the n, by definition, is equal to the limit. And I changed this to delta x this time for instead of h, just because it's what I have in my notes, and just change things up a little bit. Keep you on your toes. Okay, so limit of as delta x approaches 0, it's like h, x plus your delta x, so just a small increment, to the n, minus x to the n, all over delta x, because that's what it is, right? That's your x to the n. Now I'm actually doing this is the definition, right? It's f of x plus delta x minus x over delta x. So now what I need to do, now this is actually not obvious, but I need to apply the binomial theorem to expand that out. Okay, that's so we're going to use, I'll just say by the, and it's actually capitalized because it's the actual theorem, by the binomial theorem, we have this. This is equal to, so look up the binomial theorem if you have a second to do that, because this is really what it relies on, is the expansion of all this thing. It's x to the n plus n x to the n minus 1 delta x plus, and then what you get is n times n minus 1 over 2 x to the n minus 1, n minus 2 plus, and then you go down in that process, and this goes all the way down to delta x to the n minus x to the n all over delta x. So then, so this part right here, let me highlight that for you if I could find a good highlighter. So this right here is basically expanding it out using the binomial theorem. Not necessarily obvious how to do that. Okay, but that expansion is the binomial theorem. Okay, so look that up to make sure you're confirming why that works. I think normally in class I write it out, but it kind of messes up all this. There's just too much stuff going on. So look that up. And then see or notice that this guy here is going to cancel with that. So then what you have is, this is going to kind of look messy, but then what you have, oh, and I forgot to put that in there. I just didn't see it. I messed it up. This is actually a delta x squared. So that's your coefficient, x to the n minus 2, and then delta x squared. That's your next value. So it's usually done with a plus b to the n, and then you expand it out with a coefficient. So it's a to the n plus n, so it's like an n choose 1, right, that kind of thing. Okay, anyway, I keep telling you look it up because I don't have time to go through all those details right now. Okay, so then what you can do is factor out, oops, not that color, blue, the one delta x in every term. So one delta x in every term can be factored out to reduce that denominator delta x. So then what you get is the limit as delta x approaches 0 of n x to the n minus 1 plus, and then all the rest of that, n minus 1 over 2, x to the n minus 2, that was all over 2, delta x, and then every other term does have delta x in it, like that. The denominator I reduced out with this one, so this one reduces with all the rest. Now, when you do the limit as delta x approaches 0, what happens? I'll repeat myself. What happens when I take the limit of delta x as delta x approaches 0? All of these terms go to 0, right? You're left with just that. That's it. So that when you take the limit, you just get n x to the n minus 1. That proves what we were trying to show. It's exactly what we want to show, that the derivative is just this, okay, using the definition. All right, so that is important one we use all the time. You need to know and love that one. Let's go do another property and then apply it to another definition. So here's another property. This is constant multiple. So if you have d dx of c times, say, u, then you just factor out the c, and then it's just du dx. So the multiple, whatever, just comes out in front. So let me show you what that is, for example. For example, suppose I said, what's d dx of 2x to the 5th? Well, you don't really have to show this step, but basically you just pull out the 2, and then it's d dx x to the 5th, and then you just say 2 times and then 5x to the 4th, so it's just a 10 to the 4th. So in practice, you really just know, you go right to there. You just know you're going to do that product, and you just write it as that. You just 5 times 2, and then just write it. Okay, one more, try this one. F of x negative 3x squared. So what's that going to be? Not equals, don't say equals there. When you do its derivative, okay, so here don't use the definition, just apply the properties. That's just negative 6x. That's it. Okay. Okay, so let's do a couple more examples. So try these, and then I'll just show them to you. So y equal to 3 over x to the 5th. Let's see. I actually did this. Oh, yeah, that's fine. And then try that one. We'll call that one A. And then B, try this one. Y equals the square root of x to the 1 plus e. That one's a little weird, but it still works. So what you get is y prime is, well, you may want to write this as 3x to the negative 5 first. So that is going to be negative 15x to the negative 6. And most of the time we like to write that with a non-negative power. So you get this. Okay, this one's kind of strange. What you may want to do is write that as x1 plus e, and then that's raised to the 1/2. Otherwise, you have to have a different rule, which we will see. But then that is x to the 1/2 plus 1/2 e. Okay, so then when you do its derivative, it's basically 1/2 plus 1/2 e, and then x raised to the 1/2 plus 1/2 e minus 1. Crazy, huh? But you don't want to, you can't combine those. You can't simplify those at all. So that's just x to the 1/2 e minus 1/2. Okay, so if that didn't make sense, check that out again. It's not real critical. That's like totally clear at this point, but as you practice these, you'll see a bunch of them. This is the sections that you want to just do a bunch of examples to get the hang of what's going on. Okay, let's stop and do one more video. And by the way, this is going to take us all the way to 3.4. So what we're doing is 3.1, 2, and 3 all at once.